Hi guys, it's Mrs. Millison. We're going to do a combination of the Check Your Understanding on page 684, which starts talking about the M&Ms, and then it continues on the Check Your Understanding on page 687. So between these two Check Your Understandings, we'll do a complete chi-square goodness of fit test. Okay? Okay, so let's read. Whoops. Mars Incorporated reports that M&M's peanut chocolate candies are produced according to the following color distributions: 23% each of blue and orange, 15% of green and yellow, 12% of red and brown. Now, Joey bought a randomly selected bag of peanut chocolate M&Ms, okay, and counted the colors of the candies in his sample. He had 12 blue, 7 orange, 13 green, 4 yellow, 8 red, and 2 brown, okay. So first of all, I've recorded the percentage that Mars Incorporated says they should have, and Joey, what he actually has. He has 12 blue, 7 orange, 13 green, 4 yellow, 8 red, and 2 brown. Okay, so that's what Joey has. We'll talk about that more in detail. Okay, so we're going to do our hypotheses, then we're going to talk about expected counts, then we're going to calculate our chi-square statistic, and then the other Check Your Understanding asks for a, we're going to talk about the expected counts again. We're going to sketch our graph so we can find our p-value, and then we're going to come to our conclusions. So we're going to do our state plan, do, and conclude, okay? All right, so I'm going to move that up. All right, so here we go. Again, we're on pages 684 and 687. Nice little combined one. Okay, so we're going to start our hypotheses with our state. And this time our ho and our ha aren't going to be necessarily numbers. I will do one as numbers, but it's mostly words. So basically you're thinking, does Joey's bag of M&Ms follow what the company says there should be as far as the color distributions? Does he really have 23% blue, 23% orange, and so forth? Okay, so of course your ho is going to say that there's no difference, that it does follow the color distributions. Okay, so I'm going to write the company's stated color distribution for all peanut M&Ms is correct. Oops, that's color. Okay, and again, that means there's no difference. There's no difference between his bag of M&Ms and what the company says he should have as far as colors. Now, sometimes you'll see the ho written out in the proportions, okay? So basically we would just say the proportion of blue is 23, the proportion of orange is 23, and so forth. So you might see this. So the proportion of blue, the proportion of orange, the proportion of green, proportion of yellow, where am I? 0.15, the proportion of red, and the proportion of brown. Okay, that's just an alternative way of saying it. And of course, we'd have to identify P of B is the true population proportion of all blue peanut M&Ms. P sub O, letter O, would be the true population proportion of orange M&Ms. Okay, so this can get a little tedious. That's why I like to use the words. But I just want you to be familiar with that in case you see that. Okay, so of course the ha is going to say that no, my bag is different, or that the color distributions are not correct. Okay. Okay, which means they are different. So my Joey's bag doesn't follow what the company says he should have as far as each percentage of colors. Okay, so these are your words that correspond. So if you do the proportions, oh kitty, watch out, kitty. If you do the proportions, we've got to do our ha. Oh, sorry, kitty. Kitty just jumped off the table, knocked everything over. we're going to say at least 2 of these proportions are not correct, okay? 2. Okay, so again, that's just a different way of saying it. I usually do my ho and my ha like this, but I want you to be familiar with that, okay? So if at least 2 are not correct as a, of those proportions. Okay. Oh, we got to do our alpha. I don't believe it gave us an alpha, so we will just set our alpha at 5%. Okay. All right, let's do our plan. Now, this is a chi-square, so it looks like chi is like a Greek letter X. Chi-square goodness of fit test. So we're basically seeing if our bag fits fits the color distribution that it's supposed to. We abbreviate this with GOF. So you can write chi-square GOF on the AP test. That's fine. Okay. We're going to go through our conditions, of course. Random. Yeah, I think it said Joey bought a random bag. So stated a random bag of M&Ms was used. Okay. Independence, our 10% rule. Oh, how many M&Ms does he have? So how many M&Ms does he have? So we got to total all this stuff up. So he actually had 60. No, he didn't. He had 46 M&Ms. Okay. So for my independence, pretty sure there's more than 460 M&Ms, and thank goodness, right? And M&Ms are independent, relatively speaking. There we go. Okay, we don't have a normal count because this is not a normal, this will never be a normal distribution. Well, in so many words. But what we're going to do is we're actually going to do a large counts, and not necessarily in the sense of n times p and that type of thing, but more of expected counts. Okay, so what would I expect to get? Okay, now for the expected counts, let's again remember. I'm going to put my colors over here. Joey got these. So we got blue, orange, green, yellow, red, and brown. So we got 12 blue, 7 orange, 13 green, 4 yellow, 8 red, and 2 brown. That's what he actually got. Those were the observed or the actual. Okay, so this is the observed or the actual. Now, what would I expect? What would be the expected number of blue, orange, and whatever? So if we look back up here, if they said there's going to be 23% blue and orange, I just have to take 23% of 46 and see if it's close to that. I'm going to have to take 15% of 46 to figure out how many green and yellow I should have had, and then 12% of 46 to figure out how many red and brown I'm going to have. So for these two, I'm just going to do 23% of 46. For the green and the yellow, I'm going to do 15% of 46. And then for the red and brown, I'm going to do 12%. 12% of the 46. It just happened that these two are the same and these two are the same, but they can all be different also. Okay, so I would have expected 10.58 blue and orange. I would have expected 6.9 green and yellow M&Ms, and then 5.52 red or brown M&Ms. If I add those up, it should also equal 46, okay, just to do a quick little check. And they do. So I figure, that doesn't look that different. I would expect about 10 or 11, and I got 12. Here I would expect 10 or 11, and I only got 7. Here I would expect about 7, 6.9, but I got 13. So that seems really far. That seems really far, too. That seems really far. I don't know. That seems okay. So, did my bag of M&Ms really follow the distribution? I don't know. I'm like, I don't know. Maybe a little iffy. Okay. The important thing is all these expected counts have to be greater than or equal to 5. And they are. So that's what we're going to say under our large counts or expected counts condition. We're going to say all expected counts are greater than or equal to 5. Okay. Don't make that statement without showing your expected counts. Okay, if you don't have this and you say that, there's no backup for you to say that. So you've got to show your expected numbers. Okay? All right, that's it for the plan. Let's do the do. Actually, I'm going to try this out. The do is a little different, but exactly the same, you know? Okay, we're not going to have a t or a z. We're going to have a chi-square statistic, okay? So kind of a chi-square score, if you want to call it that. And the formula for chi-square is we're going to sum up the equation observed minus expected squared all over expected, okay? Looks really scary. It's really not that bad. We have 1, 2, 3. We have 6 color categories. So I'm going to calculate my chi-square. Let's see, 1, 2, 3, 4. Oh, can I squish them all in here? Okay. So for the first one, for blue, observed minus expected. I observed 12 and I expect 10.58. I'm going to square it and divide by 10.58. For the orange, I observed 7 and I expect 10.58. Green, I observed 13, but I only expected 9. Yellow, I observed 4 and I expected 6.9. Did I say 9? 6.9. And then red, and blue. Oh, let me squish that in there. Oops, sorry. Okay. So if I stick each one of these in the calculator individually, okay, I stick each one of these in the calculator individually, this will get me 0.191. This will get me 1.211. This part will get me 5.393. Let's see, 1.219, 1.114, and 2.245. Add all those up, and my chi-square statistic, that's a terrible chi-square, is 11.372. Okay? Now I'm going to show you how to do it in the calculator in a second. All right? So after I add all those up, so again, this is sort of like my t and my z-score. So I need to use that to find my p-value. Okay? So I'm going to do that in the calculator. And what I have under my second vars, not normal CDF for using a z-score, not t-CDF for using a t-score, but I have chi-square CDF. So I'm going to use chi-square CDF in the calculator. Think about this on a curve, okay? It's a little different curve. It's not so symmetrical. So 11 would be over here. You know, it's just a higher number. So I'm going to go from 11.372 to a gazillion. Now, degree of freedom. Degree of freedom is number of categories minus 1. So I have 1, 2, 3, 4, 5, 6. I have 6 categories, so my degree of freedom is 5. And then I will paste. Oh, whoops. So there's my p-value. I'm going to write this down right here. So my p is 0.0445. Okay? Now let me show you how to do all this in the calculator. Okay? Now we have a, if you go to stat test, go all the way down to the second page, we have a chi-square goodness of fit test right there. And when I hit that, it tells me I should put my observed values in list 1 and my expected values in list 2. Okay, so I'm going to put some stuff in list 1 and list 2. So these are my observed and these are my expected. So let's go, first of all, let's go to list 1 and list 2. So observed, right, and expected. Oops. Okay. So observed and expected. So now I can go back to my, go back to my tests. I'm going to scroll up from the bottom. It gets me there a little faster. So there's my chi-square goodness of fit. So yes, I have my observed in list 1 and I have my expected in list 2. Oh, and look, my degree of freedom is 5. It didn't know that. That's a default. Make sure that's right. Okay. I'm going to draw it first so you can see it, so you can see the curve, and then we're going to calculate it so you can see some other stuff. So again, a chi-square curve isn't symmetrical unless your sample size is really, really big, and then it becomes symmetrical. It becomes more symmetrical. But there we go. I can check my chi-square statistic. So 11.372, whatever. And there's my p-value, 0.0445. So to be quite honest, I never use inverse vars or second vars chi-square CDF. Once I get all my observed and my expected, I just run the test, okay? So let me show you now. If you go and run the chi-square test again, oops, and you calculate, it's going to give you your chi-square statistic. It's going to give you your p-value, and of course your degree of freedom. And then this part right here gives you all these pieces to your chi-square statistic. So there's my 0.191. There's my 1.211, 5.393, 1.219, 1.114. I'm just scrolling over. I'm scrolling over, guys. And 2.245, okay? So I can kind of get everything. The only thing I really had to write out was my equation, and we'll talk about that in class and how you can shortcut that. But I can get all this from the calculator. So I do. I never do chi-square CDF. I just run it all in the calculator, okay? So again, I'm just scrolling on my scroll bar here to go back and forth, okay? The rest is the same old, same old. Compare it to alpha. What would we do, a 0.5? And I do believe that is correct. So we will say in our conclusion, the p-value is 0.0445 is less than alpha of 5, therefore it is statistically significant at the 5% alpha level, so we can reject the HO. So if we reject the HO, we do have convincing evidence that the company's stated color distribution for all peanut M&Ms is not correct. So our bag, we have evidence that perhaps their distributions are incorrect because my bag didn't follow it, or Joey's bag. Okay, so let me write that out. Nope, significant. Sorry. So we can reject the HO. We have convincing evidence that the company's distribution, stated color distribution, I'm looking at my HA here, or stated color for all peanut M&Ms is not correct. Okay. Now the last thing we have to do is a little follow-up analysis. So if especially since we rejected the HO and we say that our we don't believe M&Ms do follow that color distribution that the company says, what color M&M really made the test strong enough so that we could reject the HO. So which one of these differences was really the greatest, okay? All we have to do is go up here and look at our chi-square components. Whichever chi-square component has the largest number, it means it was the largest distance, okay? So whatever this third one was, I believe it was green, that those green M&Ms had the biggest impact. So I'm going to say the green M&Ms had the most influence on my significance test since it had the largest chi-square component. The green M&Ms. Okay. Now, if I hadn't rejected the HO, I probably wouldn't care about a follow-up analysis, because if I had failed to reject the HO, I would have said everything was good, and who cares, who cares how it got impacted, because nothing impacted because I didn't reject the HO. Anyway, so again, go up and look at your chi-square components. The one with the largest has the greatest impact. So we figure which one was 13. That was the green. Okay? Okay, that's it for chi-square goodness of fit test. Okay, see you next time.